Hi everyone. So in this video, we're going to try to tackle two concepts, the covalent bonds and also this idea of ionic character. So with covalent bonds, what this means is that instead of a transfer of atoms, a transfer of electrons, electrons are being shared. And the nicest way, the most elegant way to illustrate this, I think, is the Lewis dot model. This was developed by Gilbert Lewis. And uh, the way it works is we can look at the electron configuration of something like chlorine. So chlorine has an electron configuration that is neon plus the 3s2, so the filled s orbital, and then a 3p5, very close to having the p orbital filled with 6 electrons, but not quite. It's just got 5 electrons instead of 6. So in the Lewis dot model, what you do is you look at these outermost electrons and you put a dot. There are 7 of them. You put 2 on each side. So we'll just put 2 over here, 2 over here, or up to 2 on each side. We've drawn 2, 4, 6. There's only 7 electrons here, 2 in the s orbital, 5 in the p orbital. So we draw 7 electrons around chlorine like that. And so we can consider another chlorine, and we'll put in 2 electrons, 2 electrons, 2 electrons, and not by accident, I'm going to put the lone electron on this side. It's rather arbitrary, but what I want you to be able to see is something that Lewis discussed over 100 years ago, that a way to think about bonding and filling these electron orbitals in the outermost shells is that you can bring these 2 chlorine atoms together so that they can bond by sharing 2 of their electrons. Let's put those electrons in a different color. So it'd be this guy here and this guy here. And so by bringing these 2 atoms together, I think I want to draw that in white. Then we have a covalent bond. So in this case, it's not a transfer of an electron from one to the other. Both chlorine atoms are in the -1 state. Well, we usually leave off the 1, just call it a negative. So the chlorine atoms have a negative charge overall. They don't want to give up an electron. They want to acquire an electron. But the way they will achieve this -1 charge is by sharing an electron between them. And so together, that gives us chlorine gas, or Cl2. So that's the idea of covalent bonds and sharing of electrons. What we're going to do now is move on to ionic character, because it's part and parcel of this discussion of sharing electrons. So with ionic character, comes a recognition that bonds are not purely ionic or covalent. There's a little bit of both charge transfer and sharing of electrons that happens in almost all kinds of bonding. And there are a couple different kinds of equations. The one that we'll use is one where we calculate ionic character as a function of electron negativity. So we have 1 minus E raised to the -1/4 power multiplied by XA minus X sub B, and that whole quantity is squared. So this whole thing here is being raised to, is the exponent above E. And XA and XB are electronegativities. So electronegativities of atoms A and B that are being bonded together to one another. So we take their electronegativities, look at their difference, square that difference, multiply by -1/4, take that whole amount, raise it to raise E to that power, and then 1 minus that is the so-called ionic character. Let's do a couple of examples. So for the case of sodium, if you look in your periodic chart, sodium has an electronegativity of 1, while chlorine has an electronegativity of 2.9. So it doesn't matter which one we call XA or XB. So if we'll call this one XA, this bottom one XB, then we get difference of XA minus XB of minus 1.9. The negative sign doesn't matter because we're going to square this. And when we square it, that's going to become 3.61. And if we reverse these and call this one XA and this one XB, we'd still get the same answer. So whether we carry the negative sign through or not, it really doesn't matter, because by squaring it, we're going to get rid of that negative sign. So X here, the XA minus XB part, when it's squared, is equal to 3.61. If we now multiply that by minus 1/4, then this whole thing is equal to minus 0.9025 approximately. This negative sign will carry through. If we take E and raise it to the minus, we need a 0 there, 0.9025, then that'll give us a value of 0.4055, and then 1 minus 0.4055 is equal to 0.594. And if we multiply by 100, then that means we get 59.4% for our ionic character. This means that for the sodium-chlorine bond, sodium and chlorine bond together in a way that it is 59.4% ionic. Right? So when we look at bonding of different elements, there's really no such thing as a purely covalent or a purely ionic bond. These are very handy concepts. But the way atoms share and transfer electrons is a little more complex than that. And this equation of ionic character is a way of getting at that kind of complexity. And so when we look at something like sodium and chlorine, we think of them as a salt, and they're far away from each other on the periodic table. But there is a certain amount of covalent character. Covalent character would be the other part of this. So the opposite of the ionic character, or the balance of it, was this part over here. So if ionic character is 59.4%, then that means the covalent character is 40.55% approximately. I'm carrying through a lot of the decimals, and some of there are going to be some rounding errors if you just keep track of what's written here. So this bond here is not purely ionic. It's mostly ionic, but a good fraction of it is covalent as well.